Hello everyone. In today's tutorial, we're going to break down the HCS12 CPU architecture, register by register, flag by flag, and instruction by instruction. So in this diagram here that I put together, we've got the CPU with its registers, the memory map, and the condition code register with all its flags. By the end of this video, you'll understand exactly what each part does. So let's start on top. This is the CPU, which is known as the brain of the microcontroller. Inside it, we have three main components. First, the ALU, or the arithmetic logic unit. The arithmetic logic unit, this is where all the math and logic operations happen. If you're doing addition, subtraction, comparison, bitwise operations, it all happens here. Second, the control unit. This is the traffic cop. It decodes instructions and coordinates everything. And third, the focus of today's video are the registers. These are the CPU's high-speed storage locations. Data moves between memory and registers, gets processed by the ALU, and goes back. So let's go through each register one by one. So first we have the accumulator. This is the ALU's primary workspace. When the CPU needs to add two numbers, it puts one in the accumulator, adds the other, and the result stays in the accumulator. As we can see, the HCS12 has two 8-bit accumulators, accumulator A and accumulator B. They can also be combined into 16-bit accumulator called D, where A becomes the high byte and B becomes the low byte. Next is the program counter. This register holds the address of the next instruction to be executed, so it always points to the next instruction. The PC guides the fetch, decode, execute cycle, as we can see at the bottom here. It fetches an instruction from the address it points to, then auto-increment to the next address. In this example shown here, the program counter starts at 2000, then moves to 2003, then 2005, and so on. Next, we have the index registers X and Y. These are used for indexed addressing. They point to the base address of arrays or data structures. So you can add an offset to the index register to access specific elements. For example, if X points to the start of an array, then X plus 2 gets you to the third element. In this example, for example, we're not using any LDX, so they stay at 0, 0, 0, 0. Fourth, we have the stack pointer. The stack pointer manages the stack. It works on the principle of last in, first out data structure, known as LIFO. The stack pointer points to the top of the stack. When you push data onto the stack pointer decreases. When you pop data off, the stack pointer increases. And finally, we have the condition code register, known as CCR. This is the status board of the CPU. It has 8 flags. We're gonna get to learn more about them, but there are the carry or borrow. It's set on a carry from the most significant bit, or borrow and subtraction. We have the V, which is the overflow flag. It's set when the result is out of range, or if we add two negative values, numbers, and then we get a positive number, or vice versa, when we add two positive numbers and we get negative number. The zero flag, this is set when the result from a specific instruction is 0. The negative flag, this is set when the MSB most significant bit, or bit number 7, is 1, because for number 1 we get signed number, so this is a negative number. We have the half carry. This is set from bit 3 to bit 4. We have the interrupt mask. It's set. When set, it disables the maskable interrupts. And then we have the X flag. It's set. When it's set, it disables the XI RQ interrupts. And then we have the stop disable. When cleared, it allows stop instruction or standby mode. So these are the registers of HCS12. As we saw, it has two 8-bit accumulators A and B. They can be combined to form a 16-bit register, which is called a double accumulator D. We have the index registers X and Y, each is 16 bits. We have the stack pointer, 16-bit. The program counter is 16-bit. And we have the condition code registers. The 8 we just mentioned are mentioned here. So next, let's take this assembly code example. and then try to solve it. We initialize a sum variable. dc.b tells us that this is of a size of 1 byte, and then we initialize it with 0 variable. And then we're gonna get this sum stored at location 1000 in the memory. And then after this, we initialize the stack pointer at the address of 2000. And then we have these instructions. So let's start by writing the machine code for each instruction. So in this column here, let's write the machine code. And then in this area here, I'm gonna write the memory addresses and what we have at each address. So we start at 1000, and then we have some addresses here, and then we go from starting at 2000. So each microcontroller that you use, it has an instruction glossary we can refer to obtain our machine code. So this is the instruction glossary for HCS12 microcontroller. So we start by LDS. So we can search in it as LDS, and then as we can see here. Later I'm gonna make a dedicated video about the address mode, but for now, for this example, anytime we see a hashtag before the number, this is an immediate addressing mode. So for the first instruction, the object code is CFJJKK. So let's go back here. So the machine code for this specific instruction, as we saw, it's CF. And all of these, when I put the $, these are hex numbers, hexadecimal. And then the JJKK are going to be obtained from here. 20 are for JJ and 00 for KK. So the machine code for this instruction will be CF2000. So we can write the content of each memory address. So at 2000, the content is CF. And then now it'll increment by 1. 2001, we have 20 in hexadecimal. And then at 2002, the content is 00. So let's move to the next instruction. The next instruction says LDAA. That means load accumulator A with a value of 25. So let's obtain the machine code for this instruction. So we can go to the instruction glossary and then search for LDAA. And then we saw the hashtag in our assembly instruction. That means it's in immediate addressing mode. So the object code is 86II. So the machine code for the next instruction is 86. And then II will be 25. So now we can fill the content in memory. So next will be 2003. The content is 86 in hexadecimal. And then at 2004, we have 25. So next we can move to the next instruction. What it says, add 34 to accumulator A. So let's get the machine code first, and then later in this column, we can obtain the value of what's inside accumulator A after each instruction, how it updates. But for now, let's stick to the machine code first. So let's go to add A, and then we see the hashtag. It's in immediate addressing mode, and let's get the machine code for it. So add A. In immediate addressing mode, the object code is 8BII. So that's going to be 8B. And then II, it's the number 34. The next instruction is the same. We're adding 11 to accumulator A. So add A. In immediate addressing mode, the machine code will be 8B. And then the II will be 11. So let's fill the content in memory. So we're at 25. Next, at 2005, the content is 8B. Next, we increment by 1, so it's 2006. And then the content is 34. Next, at 2007, the content is 8B, and then next, 2008, the content is 11. Next, also ADDA, we're adding decimal number 18 because we don't see there's no $sign in front of 18. So the machine code will be 8B, and then 18 is number 12 in hexadecimal. So this will be 8B 12. So let's fill the content in memory. So the next will be 2009, and then the content is 8B. Next will be 2010, but 10 in hexadecimal is letter A. So we have 2000A. The content of memory address 2000A is 12. So let's move to the next instruction. ADDA, we're adding the binary number 00001110 to accumulator A. So for ADDA, the object code or the machine code is 8B. And then this value here, 0001110, we need to find it in hexadecimal. So 00001110. This is 0 in hexadecimal. And this one we have 2 to the power 0, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8. If we add 8 plus 2 plus 4, this is 14. 14 in hexadecimal is E. So this will be 8B 0E. And then the content in memory, I think I need some more space here. So we have next one is 2000B, and the content is 8B. And then next one is 2000C. And then the content is 0E. And next we have STAA, store, result, and sum, at memory address 1000. So to store the result, we need to know the value of A. So in this one, let's see how value of A will update after every instruction. So LDS, we initialize stack pointer at 2000. Here we don't know the value of A. And then we have load, first instruction, load accumulator A with a value of 25. So at this instruction, inside the accumulator A, we have number 25 in hexadecimal. And then next instruction, we say add 34 to accumulator A. So it was initially 25 in hex, and then we add 34. So this will give us 59. Also, it's better to convert to binary and then add them and then convert to decimal if it's hard, but this one is easy. So A will be 59 after this instruction is executed. Next instruction, we say add 11. So we have 59 and then we add 11. So 9 plus 1 is 10, 10 is A, and then 5 plus 1 is 6. So A is 6A after this instruction is executed. Next, we add 18, which is 12 in hexadecimal. So we have 6A plus 12. Let's convert them to binary. So 6 is 0, 1, 1, 0. For easiness, you can put for 4 bits, you have 8, 4, 2, and 1. So to make 6, you need to set these 2 bits to 1. 4 plus 2 is 6. And then A is number 10. So to get 10, you need this 8 plus 2. So in binary will be 1, 0, 1, 0. 12, number 1 is 0, 0, 0, 1. And then number 2 is just this bit. So 0, 0, 1, 0. Now if we add these two binary, we get 0. 1 plus 1 is 0 with carry 1. 1 plus 0 plus 0 is 1. 1 here, 1, 1, 1, 0. Now we can convert to hexadecimal. So 0, 1, 1, 1 is, you have 4 plus 2, 6 plus 1 is 7. 7 in decimal is 7 in hexadecimal. And then from these 4 bits, we get 8 plus 4, which is 12. 12 is letter C in hexadecimal. So after this instruction is executed, accumulator A will have value of 7C. And then after this instruction, we add 00001110, which is in hexadecimal is 0E. So we're gonna add 7C, I'm gonna write it here, plus 0E. To add them, it's better to convert them to binary. So number 7, you get 4 plus 2 plus 1, which is 0, 1, 1, 1. And letter C, we have it here, 1, 1, 0, 0. 0E, the 0 is 0, 0, 0, 0 and 4 bits. And then letter E is from here 1, 1, 1, 0. Now we can add them. 0 plus 0 is 0. 1, you get 0 with carry 1. 1 plus 1 plus 1 is 1 with carry 1. 1 plus 1 plus 0 is 0 with carry 1. 0 with carry 1. 0 with carry 1, and then 1. So now we can convert to hexadecimal. From these 4 bits to the left, we get 8. And then here we have 8 plus 2 is 10, which is letter A in hexadecimal. So after this instruction is executed, A will be 8A in hexadecimal. And then now let's find the machine code for STAA from our instruction glossary. So STAA, this is extended addressing mode because it's going to get stored at memory address 1000, which is a size of 16. So in extended, we have 7A HHLL. So the machine code will be 7A. And then for those letters, we're going to get 1000. So it'll be 7A 1000. Now we can write the content of the memory. So after C, we have 2000D will be 7A, which is this one here. And then make some more space. After D, we have the memory address 2000E, and the content is 10. And then after that, we have 2000F, and the content is 00. So A here is still 8A, but it gets stored at the memory address of 1000. So if we go back, so after executing this entire program, the content here will be 8A. And then after this, we jump to an infinite loop. So basically, we stay here forever. So this is it. In the next video, we can expand and try to figure out the CCR flags after each instruction is executed. I hope this video was helpful. Thanks for watching.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.